guys, this is Donnie here, and I'm going to be doing a quick overview of number systems for my 1025 class. This is the first time I've ever done a YouTube lecture for this, actually, because I've almost always done it in class. But because of the pandemic and the move to online classes, I'm going to have to give this a try online. It's going to be a little weird because this is kind of a lecture that usually has a lot of questions and a lot of interactivity, but I'll give it a shot. So we start off a little philosophical. The purpose of this entire lecture is to describe how do we store a quantity in a computer, because we have to start with numbers in order to get anything more complicated. So we start off with the idea of quantities and machines. So how do we tell a machine to store a certain quantity or keep track of a number, if you will? So it all starts with obviously math, and to do that we have to examine kind of what we learned when we were in grade school. So we have decided upon a certain number system. We use the decimal number system right now, and in the decimal system we have a particular symbol that looks like this. And this is, of course, the number we all know and love as 5. But I mean, if you really look at it and like kind of try to forget everything you know, it's really just like a random symbol. It's like a horizontal line and a vertical line and then a little swirl at the bottom, and it's like it doesn't really mean anything. It's just a symbol that we've assigned a meaning to. So if you keep that in mind, it's important because not all number systems are the same. This just happens to be the the symbol that represents the quantity of 5. Um, and what I mean by that is I want you to go beyond your normal understanding of the idea of the number 5 and really think about it as the quantity 5. So that symbol really represents to us an amount of things, a quantity of things. So in this case, we can visually see there are 5 boxes. That's what 5 means. It means it's that many things. So really want to think about values. I could call it a value, I could call it an integer, I could call it a number. But what I really want you to focus on is the idea of quantity, because that's really what's probably the most important concept as to what a number actually means to a computer. So if we go a little more complicated and we take several of the symbols in the decimal system that we know, we put 4 of them next to each other, and right away we say, oh, that's 5,280. And I could ask you, hey, what does 5,280 feet look like? And you would immediately in your mind, almost instantaneously have kind of like the idea of what a mile looks like, how long it is. Not exactly, but you have a pretty damn good idea. Just like if I asked you, what does a pile of, 50 apples look like, you would have a pretty good idea of what that looked like. Just from looking at, a number. Even if it was a pretty bigger number. If I asked you what a pile of 300 apples looks like, you'd have a pretty good idea. So the point of all this is that we think that this is like really obvious because we just look at 5,280 and it's like, oh yeah, that's how many it is. But we don't really comprehend all of the mathematics that our brain is doing in order to take all 4 of those symbols and come up with a single quantity. And the reason we have to break this down and really go into the rigorous details of how it's doing that math, or at least what math is involved in computing that, is so that we can use the same exact process with a different number system. And that's important because computers do not use the decimal system, they use the binary system. So, moving on. So this is the mathematics that's involved in our brain when we look at those 4 symbols, 5280, and we think to ourselves, oh, that's 5. Obviously, that's 5,280 feet. So it all boils down to us learning when we were little kids that the first column on the right is the ones column, and then the next column is the tens column, and the column after that is the hundreds column, and the column after that is the thousands column. So what we're doing in our mind really is we're taking each one of those symbols, the 5, the 2, the 8, and the 0. We are like just like we did with just the five, we're associating each one of those symbols with a quantity. We know how many five is, we know how many things two is, we know how many things eight is, and obviously zero is no things. And for each one of those, we take the multipliers, or the column weight, if you will, that we have memorized because we were taught these things, like as children. We were just taught, like, the ones column, the tens column, the hundreds column, the thousands column, and we take those ideas and we combine them together and multiply straight down for each column. So if we start on the left, we say, oh, I recognize this as five things, but that five happens to be in the thousands column. So it's not actually five things. It's 5 times 1,000. It's 5,000 things. So we combine those two things that we've learned, that this symbol represents five things, but that it's in the thousands column. Therefore, we have to multiply it times 1,000. And that piece of arithmetic, combining those two pieces of knowledge, performing arithmetic on them as a multiplication, comes up with the value of 5,000. So that's kind of like three things that are happening in our brain just to come up with this number. And if we repeat that among the columns, we have, we think the 2 represents two things. It's in the hundreds column, therefore it's actually 200 things. We perform that for every one of them, and we come up with these four numbers: 5,280 and 0. So what we've done is we've memorized the column values. We've memorized what quantity each symbol represents, and then we've multiplied down. Multiplied this, the 1,000 times 5. We've multiplied the 100 times 2. We've multiplied the 10 times 8. And multiplied the 1 times 0. So that's when I say multiply down, I'm saying for each column we multiply the actual quantity times the weight, or the multiplier, or whatever you want to call it. And the last thing that we have to do is we have to add across. So what I usually say is, to understand number systems, you have to understand what each symbol is worth. Like, this is worth 5, this is worth 2. And then, in terms of quantity, you have to memorize what the multipliers are for each column. And then you have to multiply down and add across. And that's it. Okay, so those are like the steps. You have to know what the columns are worth, you have to know what the quantities are worth, you have to multiply down, you have to add across. So obviously if you add 5,000 plus 200 plus 80, you get 5,280. So that all of that stuff, like the translation of visualizing this symbol into a quantity, multiplying it times recognizing that it's in a certain position, and multiplying it times another number to come up with the product, doing that for every single column, and then adding the sum of all of those values is actually the way that our brain does all the math to come up with the total quantity that these four symbols put together is worth. So that's a lot of math. It comes easy to us because we've been using the decimal system our entire life. So when somebody asks us, when somebody puts a number in front of us, we don't even have to think about, what the number over here is worth. It's obviously worth 10,000. So if there's a 7 over here, it's obviously 70,000. We can think about that in an instant because we've been doing it our whole lives. And we think the decimal system is special. We're like, oh, it's so easy. It's just 1, 10, 100, 1,000, 10,000. But it's actually not. It's a very powerful illusion that the decimal system is special. Um, if we were using a different number system where the numbers looked crooked, and it was like, the base number was 7, and it was like just the columns looked like they were like all of this math looked impossible to do, and it took us 15 minutes to figure out what a single number was worth. Um, it's really no different. It's just that if we had been doing that since we were children, we would be able to do it just fast. Anyway, and oh yeah, the whole reason I mentioned that is because it's just an interesting factoid that the reason they chose 10 as kind of like the basis for our number system, because we use the decimal number system. DEC means 10, obviously, and the reason they chose that is because human beings have 10 digits. We have 4 or 8 fingers and 2 thumbs, which is, I guess you could just say 10 fingers if you want to make it shorter. But yeah, it's like we wanted to count things on our hands, and there's like 10 digits there. So that's the reason they chose 10. It's not because 10 is special. It's just because that's how many digits we have on our fingers. So in the number system that we use, the decimal number system, we have these columns memorized, what they're worth, 1, 10, 100, 1000. We can keep going forever, and we pretty much have them all memorized up to probably like a quadrillion, or at least a trillion. Um, but it's really necessary to understand how to come up with these numbers, just in case we have to switch to a different number system. Um, in a different number system, these would be calculated in a very specific way, the same way these are calculated, but they wouldn't be obvious. These are obvious to us because we've memorized them. In another number system, we have not memorized them, so we would not know what they are. It's going to be important to know that for computers because the computers do not use the decimal number system, they use the binary number system. Another number system we use sometimes in computer science is the hexadecimal number system, which is base 16. So it's important to understand how these mathematically are computed, just so that we can reproduce that process for different number systems. To just show you how that is computed, it's actually here. It's just I didn't put any color on it, but if I put some color, say red, um, what you do is you just take the base of the number system, which in this case is 10, and you just keep writing the number over and over and over again, 10, 10, 10, 10. And then as you go from the right to the left, you start with the number 0 and you add exponents incrementing by 1 at each step. So 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. And that is exactly how you come up with these numbers. Anything to the first power is 1. So 10 to the 0 is 1. Anything to the first power is itself, so 10 to the 1 is 10. 10 squared is 100, 10 cubed is 1,000, 10 to the fourth is 10,000, and so on and so forth. That is how you compute these numbers if you don't know them. If you do know them, then these don't matter because as long as you know them, you can multiply down and add across. So that's the important part, is that you need to know what the columns are worth so you can multiply down and add across. You need to know what the columns are worth. You need to know what the quantities, the symbols represent in quantity so that you can multiply down, add across. That is the whole thing. That is how number systems work, and that's how we do the arithmetic with the different digits in the different positions in order to come up with a complete value for a single number. So before we move on and really get into like specific examples for decimal and binary, I want to talk about a little bit about computers and why they need to use the binary number system instead of just going right into it. So um, this is going to be, I'm going to have to gloss over this a little bit quickly because our next topic, and maybe I'll do a video for that too, who knows, but our next topic is takes a really long time to talk about because it deals with the concept of analog versus digital data, and that's kind of what we're dealing with here. So just quickly, um, the world that we live in is full of analog data. That being, it's continuous and infinite. Now, I could talk about this for not hours. I could talk about this not days. I could talk about this for weeks, months, maybe even the rest of my life, because it deals with the concept of infinity, which is something that is almost impossible for a human being to comprehend if we can comprehend it at all. So if you think about how tall you are, for example, you cannot tell somebody how tall you are with exact precision. There is no way to express in the real world a perfect measurement. So in the real world, where things that we measure like distances, lengths, and things like that, even age, because an age isn't really an integer. It's not, how many years old are you. Age really is an amount of time, which is also infinite and continuous. You can't specify a perfectly precise amount of time because there's no smallest unit of measure. That being said, when we're dealing with computers, we're dealing with a finite amount of memory, a finite amount of data that we can store in a machine. So in the case of this light switch here, this basically represents a bit, which is the smallest unit of measure in a computer. In a computer, we basically want to say there's two positions. There's the on position and the off position. And if we interpret it, if we ignore the fact that, yeah, okay, there's, obviously there's an infinite amount of real positions, but if we ignore that and we just say, you know what, we're going to utilize this as a switch, and if we throw it down, it's off, and if we throw it up, it's on, and those are the two values. That's why people say zeros and ones. Like, that's why people say computers are nothing but zeros and ones, because they're just a bunch of switches that are either on or off. And the word that we use for this is a bit. So a bit is anything that has two discrete states, on or off. It doesn't matter what type of technology you use to represent the on or off state. Um, in the very beginning, with Alan Turing and the Turing machines, you could watch the movie The Imitation Game. They literally were like these little switches or little levers or things like that, that were either on or off. This one here in the middle represents the very large hard drives that most of you probably have. So like I have, this is basically a magnetized particle platter hard drive. So the way these store bits is they have, as you can see, it's kind of like a stack of platters, or disks or whatever you want to call them, and they contain an enormous amount of magnetized particles. And this little pointer thing here is called the head, and the head goes around and it magnetizes or demagnetizes each particle in order to change it from a 1 to a 0. I'm just going to be completely honest. I know nearly nothing about the actual way that solid state drives work, but luckily for me, that's not really the topic of the number systems lecture. I just wanted to give you guys an example of historically how the machine physically stores the value of the bits. Anyway, moving on. So now that we know that, I will show you basically how, starting with the decimal number system, how we kind of use everything that I just talked about to just pretty quickly do the multiply down and add across. So I'm just going to start with one number. I'll do like a million. So I'll put 5 there. So it's important to understand everything that just happened there. So first of all, 5 is one of the symbols that is in our number system, is in the decimal number system. Therefore, 5 has a real meaning. It means 5 of these. So the next question is 5 of what's? And that's where the column value comes into play. Now you don't need to have these here, if you have them memorized, which we do. But I just wanted to put them there so you can see how they were calculated. Um, a million is 10 to the 6th, and it happens to be in the 6th row. 0, 1, 2, 3, 4, 5, 6. So that's how it comes up with 5 million, and it adds across. And since that's the only number there, then the quantity that this represents, 5000000. I mean, you might be able to look at that and say, oh, that's easy. It's 5 followed by 6 zeros. It's 5 million. Like I said, we can do this in our head in decimal, but not so much when it comes to binary. So let's see. How about 30,000? So what happened there is it recognized that this means 3 of those, and we said 3 of what's, and 10,000, so that makes it 30,000. So multiply down to come up with the 5 million and 30,000, and add it across to come up with the 5 million 30,000. Now I could keep doing this, for whatever. I could say, I could put whatever numbers I want here. And if you look at this, you can say to yourself, well, oh, that's easy. That's 25,433,875. And then if you look over here, it's 25,433,875. So it's really easy for us to visualize what that was going to be. We didn't have to multiply down and add across in our mind. We could just look at this and know what it is because we're so good at it because we're doing it our whole life. However, when you get to the different number system, it is not that easy. So moving on. Before we do the same thing that we just did in a different number system, I just wanted to introduce the concept of a byte. 8 bits, you put them together and you have a byte. So that will be clear why we did that for convenience when we're using bits in the binary number system to represent um, quantities in binary. Hopefully that'll be self-evident pretty soon here in about 2 seconds. All right, so here we are finally. This is the point of all that talking. So now we are in a new world. We're in a different um, number system. We no longer have 10 symbols to work with. We only have 2 symbols because remember, uh, we all we have is a bunch of little switches or light bulbs or whatever you want to use, levers. You can use any analogy you want. Either way, the very basic unit is a bit. It's either on or it's off, and based on that, we interpret it as a quantity. So remember, we were interpreting the symbols in the decimal number system as quantities. We looked at the 5 and we said that means 5 things. But now we only have 2 choices. Either there's a thing or there's nothing. Okay? That sounds easier, right? It is easier actually. Um, but it's going to take a little bit of work for us to make the transition between binary and decimal. So, knowing that we only have these 2 symbols to work with, saying there's a thing or there's not a thing, we call this base 2 because there's 2 symbols to work with. So, the big question is, how do we come up with the column values? That is the big question in any number system. And the way you do it, like I said, is you put the base, you just repeat it over and over again, 2, 2, 2, 2, 2, 2, 2, 2. You put the exponents there, 0, 1, 2, 3, 4, 5, 6, 7, and then you do the math. Anything to the 0th power is 1, so that's 1. Anything to the first power is itself, so that's 2 to the first power is 2. 2 squared is 4, because 2 times 2 is 4. 2 cubed is 8, because 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 is 16, and so on and so forth. And you can keep going forever. Now, it just so happens that, you know, I've, you know, I have this memorized, and you should be able to also eventually. If somebody asks you what the columns are worth in decimal, you just like you say 1, 10, 100, 1,000, 10,000, 100,000, a million, and so on. You should at least be able to get up to 128 in decimals or in binary. So try to either write it down and so you can always look at it, or hang it on your wall, or do whatever you have to do to memorize it, because anytime you use binary, you need to know that at least the first 8 columns, because that's a byte is 8 bits. So if you're representing a byte, whatever you put in this first position is worth 1. This is worth 2. This is worth 4. This is worth 8. This is worth 16. So if I told you I want to know what I want to know what the number 10101101. If I if I asked you like what is that quantity in binary, there's no way that you're going to be able to do that in your head instantly like you can in decimal. Um, but if you do it one step at a time, it'll make sense. And to be honest, you'll be able to do it faster and faster. Like I can look at this and kind of quickly figure out what the value of what quantity it represents. So since I know that the biggest column is 128, I know that it's at least 128, right? So how do I know that? So it's like if I put you only have 2 choices for these numbers. You can't say 1, 2, 3, 4, 5, 6, 7, 8, 9. It's either a 0 or a 1. So the first one is a 1, and I know that's going to be 1 times 128 because we multiply down. And as you can see, it so far, 100000000. If that were the number that we were looking for, the answer would be that's 128. We do not have a 64, but we do have a 32. Put a 1 in there, and it added across, so now it's 128 plus 32, which is 160. So we continue to do that. There is nothing in the 16s column, but there is a 1 and a 1 in the 8 and the 4s column. 1, 1. So now we have 128 plus 32 plus 8 plus 4, and there's only one more, which is 173. So 10101101. Is that what I said over here? 10101101. Yes, this is actually the quantity of 173. And that is how binary works. So you can change the value of any single one of these 8 places in the byte to be a 1 or a 0, and it'll change what number it represents. But that's what I just said is the most important thing, is that given 8 bits, that is 8 things that have an on or an off state, if you set them all, each one of them, to be either on or off, you can simply look at them, you look at all 8 bits, you interpret them in this fashion, and you can come up with a number. That is the most important thing, because now we can represent numbers with physical media in a computer, right? Whether it be switches or magnetic particles or punch cards, whatever it is, we can take something physical that has 8 bits, that is 8 things that we can switch on or off, and we can represent a number. What are the constraints of the number? Well, obviously the smallest number we can represent is 0, but what's the biggest number we can represent? That would be 1, 1, 1, 1, 1, 1, 1, 1. So let's just change all these to 1s. This is the equivalent of it all being 9s in decimal. So just as the biggest 4-digit number in decimal would be 9,999, the largest number a byte can store is 11111111, which is the magical number of 255. That number is going to come back to haunt us for the rest of our lives. 255 is the largest value you can store in a single byte. I won't talk about it too much right now, but I will say if you remember any really old pieces of software, old video games, you might have seen this number come up a lot as the largest possible value for a thing. Like maybe, if you were playing a game and there was like the most powerful sword in the game, its attack power was 255. They were just trying to save space in memory by only allocating 1 byte to store the value. So this is a really simple way of thinking about it, because like once you've memorized 128, 64, 32, 16, 8, 4, 2, 1, in order to translate between basically binary and decimal, all you need to do is understand that it's multiplying down, adding across. Like if you want to do it backwards, so converting binary to decimal is pretty trivial. We just did that. Doing it backwards is a little bit weird, but it's still pretty easy. So if I said, hey, I want you to tell me what the binary representation of the number 150 is, it's pretty simple. You would just start over here and you would say, okay, I want to get to 150. Do I want a 128? Yes. And then you would say, do I want a 64? No, because I'm trying to get to 150, and 64 would, as I added across, if I put a 1 there, it would already put me 192. That's too many. So you kind of keep adding as little as possible. This would put me at 60, so I don't want that. I want to keep that as 0. That puts me at 144, which I want. So now I'm 6 away. Obviously 8 is too much because I'm 6 away. 4 is good, then I'll be 2 away. And another 1 right there gives me 150 exactly. So it's not really that hard even to convert from binary to decimal. So you basically use the same system of multiplying down, adding across, trying to just make sure that you start from the highest column value so that you don't go over the number that you're trying to find. But it's still the same thing. Multiply down, add across. And the key is understanding in normal number systems, it's a combination of understanding what the symbols mean in terms of quantity and also the column values. But for binary, it's extra easy because there's only 2. It's either 1 or nothing. So binary is actually the easiest number system to work with. We just haven't really done it before much. So that's too bad for us, but it's a really good number system. And to finish off, I'm just going to give one more example of another number system. Here's hexadecimal. So hexadecimal is funny because it's base 16. So there's actually more symbols than we're used to having. It goes beyond 9. It has A, B, C, D, E, and F, which um, are worth 10, 11, 12, 13, 14, and 15 respectively. So the funny thing about this is, I'm only showing you 2 columns because it gets since the nature of number systems is the higher the base, the faster the column grows exponentially. I think the fourth column in base 16 is worth 4096, so it's like you don't want to go there. So just showing 2 columns. Anything to the 0 is 1. Anything to the 1 is itself. So check this out. If I wanted to say AA, unfortunately Excel has some limitations here, so I'm just gonna have to write 10. So if this were an A and this were an A, AA in base 16 is you multiply down, you add across. So A is actually 10. So 16 times 10 is 160. 1 times 10 is 10, and you add across, and it's 170. It's as simple as that. The only weird thing is there are these new symbols that we kind of have to, this it's an example of, in a number system like this, not only do you have to memorize a new set of column multipliers, I should say. Not only do you have to memorize a new set of column multipliers, but you also have to introduce a new set of symbols in which you're not familiar and not completely familiar with what quantity they represent. This makes it extra hard to do the multiply down add across because you have to take into account both things. You have to say, like, what is A? Oh, A is 10. And what column are we in? Oh, we're in the 16th column. So it's like 2 steps of confusion. So it's like A times 16 gives you 160. Of course, you could use normal numbers here, and it might seem like it's easy, but once again, uh, this is not 55. This is 85 because this is not 5 times 10, it's 5 times 16. So which is the biggest number we can represent in hexadecimal? Well, you have to put the largest number possible, which is F. I have to write 15 because of Excel, but F is, again, the magic number of 255. So we'll talk more about this later, but the largest number you can represent in a 2-digit hexadecimal number is the same as the largest number you could put in a byte. So this is going to be useful later when we get into representation of data using hexadecimal as well as binary. So that's it. Hopefully, there was a lot of talking to really focus on really this slide right here. Like, how do you translate between decimal and binary? And I just want you to, if you get one thing out of all this, just remember that, you know, you need to know what number system you're in, what the symbols you have to work with are, and what the column multipliers are worth so that you can multiply down and add across. So, it should be very trivial if anybody comes to you and says, what's the value of 11110000? Immediately you should know that you're going to have those 4 numbers added together, and that's the answer. So for example, 0011. I'm not good at math, so 128 plus 64 plus 32 plus 16, which is 240. So this won't make you as good at computing binary quantities by sight as fast as decimal, but it sure as heck will help you understand it and a lot better and help you do it a lot faster. It really is just memorize the column multipliers and then multiply down and add across. So I know the articles that you might read are really complicated and have all these different ways of doing binary to we say bin to dec or dec to bin. That's like decimal to binary or binary to decimal. But it's really as simple as making sure the column multipliers are correctly multiply down, add across. All right, I'm going to leave it there because I've been talking for way too long, and I'm going to go have some fudge covered Oreos. Okay, bye.